Hey everyone, this video is on symmetry and cofunction identities. The first question asks us to figure out which of the six trig functions has even symmetry, has odd symmetry, or has neither symmetry. So if you remember, if I were to draw a sketch of what sine looks like, sine always starts at 0 on the axis. If there's no transformations, it always starts at 0. So this is y equals sine x right here. And if you look right here, remember the definition of an odd function graphically is that it's reflected in the origin, right? Like this part right here is flipped over on through the origin, and it's on this side over here. So this is an odd function right here. It has rotational symmetry. And then let's take a look at cosecant x. So cosecant x is going to look like this right here with some asymptotes where the x-intercepts are for sine x. And same thing right here, this has rotational symmetry. If I take this and I rotate it around, it will look just like this right here. So this is also odd. Okay, so now let's talk about cosine of x. So for cosine of x right here, remember cosine of x starts at the max and then it goes around like this right here. So this is y equals cosine of x. And that means that y equals cosine of x, if you take a look at it, it's not odd because it doesn't have rotational symmetry. I can't take this and rotate it around and have it look identical, right? So, because then it would actually look like this if it had rotational symmetry, like that, okay? It's not reflected in the origin, but it does have symmetry over the y-axis. So if I mirror this over the y-axis right here, it looks exactly the same. And remember, that's the definition of an even function. So y equals cosine of x is even. So now let's take a look at secant of x right here. And this is mirrored over the y-axis as well. So y equals secant of x is even. Okay, and then let's take a look at tangent of x. So if you remember, tangent of x has vertical asymptotes at pi over 2, 3 pi over 2, 5 pi over 2, any multiples of 2, any multiples of pi over 2, excuse me. And then it has intercepts at all multiples of pi. So this is what tangent looks like. And if you look right here, this, if I take this piece right here and try to reflect it over the y-axis, it doesn't look the same, so it doesn't have even symmetry, but it does have rotational symmetry. If I flip it around and rotate it 180 degrees, it's reflected in the origin. So y equals tangent of x has odd symmetry. And then if I were to draw out cotangent of x, it would have asymptotes where tangent has roots, and it would have roots where tangent has asymptotes. So it would look like this right here. And this is also able to be rotated around, or it's reflected in the origin. So y equals cotangent of x is also odd. Okay. Just a reminder also, so question number 2 says, use this information above to complete each symmetry identity, write each expression in terms of the original trig function. Well, just a reminder that if something is even, if a function is even, has even symmetry, f of negative x is still going to be f of x. And if it has odd symmetry, f of negative x is negative f of x. So, sine of negative theta has odd symmetry. So sine of negative theta would be negative sine theta. But let's take a look at this and see why this makes sense. So if my theta is right here, and then I have negative theta, it means it's going around the other way, but it's the same size. If you notice, the sign here and the sign here should be the same values, but this one is positive and this one is negative. And that is what this is saying right here. Okay, so now cosine of negative theta, we know that cosine is even, so f of negative x would have to just be equal to f of x. So cosine of negative theta would just have to be cosine of positive theta. Let's take a look at this right here. So if this right here was theta, if I have negative theta, it's going around this way, the cosine is always going to be the same value. They're equal to each other. Boom, done. That's what this is saying right here. And even if my theta was in quadrant 2, if I do the negative version of it right here, the cosine is still always going to be the same. On that note, let's go back to this right here. If sine of negative theta is negative sine theta, then cosecant of negative theta has to be negative cosecant of theta. If cosine of negative theta is positive cosine of theta, then secant of negative theta is positive secant of theta. And then tangent of negative theta, tangent is odd. So that means that tangent of negative theta has to be negative tangent of theta. But that should, again, make sense to you because if this is theta right here, tangent is positive in this quadrant right here, y over x. If I have a negative theta, same exact value, I'm going in the opposite direction. Now tangent would be negative, okay? And then the same thing is true for cotangents. So that's all the information about symmetry. Now we're going to talk about cofunction identities right here, but I want to develop a sense of understanding of what's happening here. So in this question right here, question 3a, it asks us to find the cosine of angle A. So here's angle A. Cosine is always going to be adjacent over hypotenuse. So that means that the cosine of A is 4 over 5. And then here, it asks us to find the cosine of B next. And the cosine of B is adjacent over hypotenuse. So cosine of B would be 3 over 5. Now it asks us to find the sine of angle A, and if angle is A is up here, cosine is opposite over hypotenuse. And then the sine of angle B right here, sine is opposite over hypotenuse. And I color-coded this on purpose for you to see that these two values are equal and that these two values are equal. And they will always be equal regardless of what the values are on my right triangle. But then it asks me here to write a general rule that summarizes the relationship between two acute angles of a right triangle. So in any right triangle right here, regardless of what the angles are, we always know that A plus B plus C would equal 180 because we always know that the angles in a triangle always equal 180. But we also know that C is 90. So this would be A plus B plus 90 equals 180. So that means that A plus B would always equal 90. Well, what does that mean? That tells us that A is 90 minus B, and that B is 90 degrees minus A. So what does that tell me right here? If you notice right here, we know that the cosine of A is equal to the sine of B. But we can rewrite B as 90 minus A. So we can say that the cosine of A is equal to the sine of 90 minus A. And then if you look right here, we also know that the sine of A is equal to the cosine of B. But we can rewrite this B right here again as 90 minus A. So that means that the sine of A is equal to the cosine of 90 minus A. So let's write this out again right here. This means that the cosine of A is equal to the sine of 90 minus A. The sine of A is equal to the cosine of 90 minus B. Okay, so this right here, these angles right here are called complementary angles. So that's why these are called cofunctions right here, because cofunctions comes from the word complementary. So right here, sine of A is equal to the cosine of 90 minus, sorry, I meant to say A right here. Sine of A is equal to the cosine of 90 minus A. So sine of A is equal to the cosine of the complementary angle. That's what we're saying right here, okay? But also it's really important that you remember to do this in radians as well. So we can also say that the cosine of A is equal to the sine of 90 degrees in radians is pi over 2, and that the sine of A is equal to the cosine of 90 degrees is pi over 2 again, okay? So how can we put this to use? Well, we can now say that the cosine of 48 degrees, I can automatically say is equal to the sine of 90 minus 48 degrees, or the sine of 42 degrees, okay? I'm going to show you one last time in a triangle why this works, and then after that, I'm not going to do it for every single triangle, okay? So if this right here is 48 degrees, we know that this has to be 42 degrees. And the cosine is the adjacent over the hypotenuse. But as soon as I start to do the sine of this angle right here, the adjacent now becomes the opposite, but it's still the same side length. So they're still going to be equal to each other. Okay? All right, so now this one right here, the sine of pi over 3 is going to equal the cosine of pi over 2 minus pi over 3, right? Because again, this is like 90 degrees, so I'm doing 90 minus the angle. Get a common denominator. So this means right here that the sine of pi over 3 is the same thing as the cosine of pi over 6. Okay? We know that from the unit circle as well, right? If I have the unit circle, the sine of pi over 3 is root 3 over 2. The cosine of pi over 6 is root 3 over 2. We know that those are the same ratios as each other. Okay, next one, cosecant. The cofunction for it is secant, and then I'm going to do 90 minus 32. So this should be secant of 58 degrees. Okay, and then cotangent, its cofunction is just tangent, and then we'll do pi over 2 minus pi over 5. So I'll get here tangent of 5 pi over 10 minus 2 pi over 10, just getting my common denominator. So this would be the tangent of 3 pi over 10. And I am done with these questions right here. Okay, so some periodic identities. If I take a sine function, which completes a full cycle in 2 pi, right here. So if I were to do a shift over of 2 pi, it would be the exact same function, like I haven't changed anything. Or if I were to shift everything to the left over by 2 pi, it would still be the exact same function right here. So the periodic identity is just saying sine of theta is equal to sine plus 2 pi. Okay, same thing is true for cosine of theta, right? If I take everything and I shift it over by 2 pi right here to the right, it would look exactly the same. Or if I shift it over by 2 pi to the left, I guess this should be negative here, it would still look exactly the same. So this means that cosine of theta is equal to cosine of theta plus 2 pi. Okay, and then lastly, tangent of theta right here looks like this. But then if and this is from negative pi over 2 to positive pi over 2. If you notice right here, the period of tangent is just 1 pi. Like the typical period of tangent is just 1 pi right here. So then if I shift everything over by 1 pi right here, this negative pi over 2 would start at pi over 2, and then it would look exactly the same. Or if I shift everything to the left by negative pi, I'd be at negative 3 pi over 2. And then this would also look the same. So this one's a little bit different. This one is saying that the tangent of theta is equal to the tangent of theta plus pi. So these are periodic identities. And obviously, it could be any multiple of these values here. So I also know that sine of theta is equal to sine of theta plus 4 pi or minus 10 pi. Same thing for cosine. I know that cosine of theta is equal to cosine of theta plus 8 pi or minus 6 pi. It has to be a multiple of 2 though, so I can't say like 5 pi, but this could be any multiple of 5, any multiple of pi, excuse me, and it would work.